So we have already covered chapter number 4. Now we are on chapter number 5, which is related to second law of thermodynamics. Do you have any idea what that second law of thermodynamics is? From your elementary physics courses, you might have heard about it. Any guess? Sorry? Energy cannot be created nor destroyed. That is something something else. Any other idea? Come on, you have a fair idea. Let me tell you, you should have a fair idea at least. Yeah, you can say so. Yeah, I mean, that's a crude definition of it. You can say so. Any other thing? That's a nice description. I mean, so that is generally accepted, one of the generally accepted statements. Okay. So let me tell you what is the reason for looking for this second law of thermodynamics first, because if you talk about first law of thermodynamics, that was something about law of conservation of energy. Okay, so whatever you are getting in and it's going out, that would cause the total change inside the control volume or your system. So that is something which is law of conservation of energy. Now the point is, why do you need this second law of thermodynamics? Okay, there are few questions which need to be addressed. Now, for example, if I say that you have a hot body with temperature T1 and you have a cold body with temperature T2. So T1 is greater than T2. So what would be the direction of heat? It would go from T1 to T2. Is it? Now the point is that heat flows due to temperature difference, not T1 and T2 in their individual capacity, not T1 and T2. That flows due to what? Delta T, the difference in their temperature. Now the point is, it can be reversed. Does it change anything with the first law of thermodynamics? The quantity remains the same. It does not change any kind of, you can say it does not make any kind of change in first law of thermodynamics. The quantity remains the same, the amount of energy which is being transferred from one place to the other, because it is, that transfer is occurring due to that delta T, so it's going there, right? So you can say that amount of energy or law of conservation of energy is good for both the cases. Why? Because the amount of energy transferred from one body to the other, that is depending on what? Delta T. Okay. So now the point is, how you would know that it would go from higher temperature to the lower temperature. It is something which we experience, which we observe, right? But the question is, again, from the engineering perspective, how would you quantify it? And how would you use that knowledge to devise or design your engineering systems? Okay, so it means first law of thermodynamics doesn't give you any information about the direction of heat transfer. It only tells you something about what? The quantities, the conservation of quantities, their magnitudes. It doesn't give you any information whether heat would be flowing from right to left or left to right or where to where. No information at all, right? So to handle those kind of questions, you need second law of thermodynamics. The second question. For example, you all know about heat engines, although I would talk about that in detail after a short while, but just to introduce you with the concept, and still I am talking about the question, why do we need that second law of thermodynamics? you have a heat source, and let's say there are two temperatures. For example, these are two bodies. Just consider this example. Now I am just talking about the real case, which just talks about this one. Heat is going from the higher temperature to the lower temperature, and the point is, okay, it is natural to have the heat flowing from higher temperature to the lower temperature, but should it be wasted like this? Heat is flowing from one place to the other. You can just see that water would be flowing from the higher temperature to the lower temperature, or the things would be moving from the higher potential energy to the lower potential energy. Now what they are doing, they are basically transforming their energy from one form to the other. Now as a human being, as an engineer, we want to use that energy. Why? Because if you don't use that energy, it would go in waste. It would go in waste, right? So what you do is, you need to transfer this energy in some form of work. You need to transfer this energy in some form of work. Now the point is, can you convert the whole amount of energy into work? Not at all. So again, the second question would be, if you cannot convert the whole amount of energy into work, what can be the maximum limit? What can be the maximum value of the heat, or maximum percentage of the heat which can be converted into work? That is again second question, right? So if you want to handle those type of questions in engineering design, you need to know what? You need to have a clear understanding on second law of thermodynamics. Okay, so second law of thermodynamics helps you understand those quantities. I hope I am clear about the need of second law of thermodynamics. Why do we need it? Is there any question about it? I think you were asking some question. It's done? Okay.
Why is it that we cannot have 100%?
Why? Okay, I would answer that. I would answer that in a short while, but just remember this thing. I would just, let me coin a term which is irreversibility. Okay, so remember this term. I would explain it in a short while. So just look at those systems. I would show you few examples. Now see, this is the body at temperature Ti, which is greater than T naught, and the atmosphere is at temperature T naught. Obviously heat would start flowing from T naught to Ti, and finally this body would also achieve the same T naught temperature, isn't it? This body would also have the same T naught temperature. Now, can you spontaneously transfer heat from atmosphere to T naught? I would use the word spontaneously. What do you mean by spontaneously? Yeah, exactly. Without any human involvement, or without any support of any external agency, or you can say automatically. Right? So spontaneously, whenever I use the word spontaneously in this context, you should understand that I am talking about what? Automatically. Okay, without any kind of external agency. So you can't transfer heat from atmosphere to this body spontaneously. Right? Now, I hope you know the literal sense of irreversibility. Irreversible, which cannot be brought back to the initial state, isn't it? What do you mean by irreversible? Something which cannot be brought back to the initial state. So this feature is known as irreversible, right? So can I say that this phenomena is irreversible? Can I say that this phenomena is irreversible? No. I'm not talking about anything external. Spontaneously, automatically. Whenever I say irreversible, can it occur? Can the irreversible process occur spontaneously? Not at all, right? So can I say this is kind of irreversibility, right? So there is a technical definition of irreversibility. If you cannot bring the system and the surrounding back to their initial state, it means you are dealing with irreversible processes. Okay, let me write down. If the system and surrounding, I am not talking about the system only, I am talking about system and surrounding, cannot be brought back to their initial states, we say that system and surrounding undergo an irreversible process. Right? They are basically, so your question that you cannot convert the whole amount of heat into work, why? Because of the irreversibility effects. Now what kind of irreversibility effects are there? I would count those at the end of this lecture. Okay. So I hope at least irreversibility is clear. So if you can bring the system back to the initial state, it means it is reversible. Just like, I hope you remember the word cycle. We talked about that in chapter number 2. Yes, cycle, where you have that kind of information with you. So that kind of process, right? So we talk about those cycles. So you can say that basically you are bringing the system back to their initial states again and again. So it is kind of what? Reversible. And why do you use those reversible processes? I hope you at least have heard about the term thermodynamic cycles, Carnot cycles, heat engine cycles, right? Refrigeration cycles. So at least you know those terms, right? So what those terms are doing, basically you put that system into a cycle. Why? Because it would increase its efficiency. It would increase its efficiency. Now how can we quantify the efficiency? We will talk about that later on. But sometimes we need to convert, or we need to devise a system which can take advantage of cycles, reversible processes. Okay, and why do we do it? To increase the efficiency of the system. Any question? I think someone.
The process will be irreversible. It will not be reversible if then we can spontaneously brought back to the initial state.
Okay, we will talk about that later on. We will talk about that later on. Till this time, I am not considering that automatic effect, right? So, just look at that one more example. There is air which is at higher pressure inside the container than that which is outside the container, which is in the atmosphere. So Pi is greater than P naught. So obviously if you just open this valve, or let's say there is a small hole inside or opening inside that lid, what would happen? Air would come out, and that process would occur spontaneously, automatically. Why? Because it is natural. The fluid would flow from higher pressure to the lower pressure. But can you bring it back into the cane? Can you bring it back into the container? Not at all. You can't do it. At least you can't do it spontaneously. It can't be done spontaneously. Right? So if it can't be done spontaneously, it means this is something which is known as irreversible process. Okay? So please remember this thing. So what kind of irreversibility can be there? Obviously once the air is coming out, there would be small amount of friction between the gas and the solid. Small amount of friction. So that friction would cause some heat to be dissipated in the environment, right? Can you bring that heat back into the air? Not at all. Like for example, if you are rubbing your hand like this, you can bring the hand back to its initial state, but you can't bring the surrounding back to its initial state. Why? Because some kind of heat has been added into the environment due to what? Friction, right? So that is why this process is irreversible, right? So friction is kind of an irreversibility. Friction is kind of an irreversibility, okay? Now similarly, this is something which is again an example. You can, let's say, take this mass from a height z1 to the ground. You can take it, but can you take the mass back to z1, let's say, spontaneously? Not at all, right? So if no kind of irreversibility, one of them is friction. I have just given you an example of friction. If no kind of irreversibility is there, you can talk about the reversible processes in some form or the other. But if there is irreversibility, you say that process has, the system or surrounding has undergone what? Irreversible process, right? So I think this concept is quite clear. So let me write down few things about second law. Just to appreciate what we are trying to learn. Whenever I use the word appreciate, I don't want to use that word in the literal sense. Appreciate means understand, okay? So where does it help us? This second law. First, predicting the direction of the process. Like for example, just look at that automobile engine. For example, you can run the engine and then you can make your wheels rotated with it, isn't it? But can you rotate the wheels and run the engine in the backward direction? Do you understand my question? My question is, you can run the engine and you can rotate the tires of your automobile, right? So direction of the process is from engine to tire. Can you reverse it? You can't reverse it, right? So that means direction of process. You can predict the direction of process from where to where you can have work transfer or energy transfer. Okay, then establishing conditions for equilibrium. Do you remember the example of that cup of a cup of coffee where you have a temperature T of T1 for the cup of coffee and you have a temperature T0 at the outside for the outside environment. So cup of coffee would attain the temperature of atmosphere. Atmosphere would not get the temperature of the cup of the coffee, isn't it? Right? So process direction. Just look at that concept. From where to where process would follow. So this is something which is condition of equilibrium, isn't it? Condition of equilibrium is what? Heat would stop flowing once both the temperatures are the same, isn't it? So that means that system has achieved an equilibrium state. No more change is there with respect to time. The system has achieved its equilibrium state, right? So if it has achieved its equilibrium state, how can you say, for example, you are looking at that cup of coffee and you say that, okay, fine, this is going to achieve this much of temperature. Whether you would talk about the change in the temperature of that cup of coffee or whether you would talk about the change in the temperature of the atmosphere, you would talk about cup of coffee. right? And why do you do that? Because you know in which direction heat would flow, right? So this is something which is about establishing conditions for equilibrium. Okay, then we would determine the best possible theoretical performance cycles, engines and other devices just like pumps or refrigerators or whatever it is. Okay, so cycles, engines and other devices. Then we can evaluate quantitatively, not only qualitatively. This is something which is qualitative, isn't it? Predicting the direction, conditions of equilibrium. This is something which is qualitative. You can just talk about that. It is going from here to here, but you can't describe it in terms of numbers. So if you can't describe it in terms of numbers, it means you are talking about what? Something which is qualitative. If you start talking about numbers, it means you are talking about quantitative analysis. Okay, so we would talk about that quantitative analysis. I mean, this is something which is qualitative, which are qualitative aspects, and these are something which are quantitative. Now you have started talking about numbers. So performance of cycles, engines and other devices, and then you have this point evaluating quantitatively. The factors that preclude the attainment of the best possible so these are the advantages of this second law, right? You can find out the answer for all those questions from this one. Okay, then there are other advantages as well, which have been the second law has been used to define a temperature scale independent of the properties of any thermometric substance. Do you remember once we talked about the Kelvin scale, I told you that somehow or the other it is related to second law of thermodynamics. I told you at that time, right? So now, because now we are going to discuss the second law of thermodynamics, at the end of this chapter we may talk about this concept. How can we use it to define the temperature scale? Or there can be another advantage. Means have been developed for evaluating properties such as internal energy and entropy in terms of properties that are more readily obtained experimentally. Do you remember we defined U as sum C multiplied by delta T, and we define H equals sum C multiplied by delta T, right? How did we define it? I mean, how can you convert an abstract kind of quantity? Internal energy is kind of an abstract quantity. You can't gauge it straight away, isn't it? You can't bring a sensor inside and you can say, okay, this is the internal energy of the system. You can't say that. So you have to convert it into a form where the property is the measurable, is something which is measurable, and then you can have some relationship with entropy or not entropy, enthalpy or internal energy. So what you have done is, this U was equal Cv delta T, so it means you have converted this quantity into something which is measurable, right? So you can use this knowledge for that purpose as well. Now let me write down those statements for second law. You would find many statements for this second law of thermodynamics, more than one. But remember, although they would show you different, they seem to talk about different systems, different thermodynamic systems, but once you check them in detail, you would see that they are equivalent. If you violate one statement, you would violate the other statement as well. Okay, so let me write down those statements. First of all, we would discuss this Clausius statement. So Clausius was a scientist who first discussed this second law, and he tried to define it. How does he describe this second law? It is impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. Now read that statement very carefully. It is impossible for any system. You can't have that kind of system with you which can operate in such a way that the sole result would be an energy transfer by heat from a cooler body to a hotter body. Let me just define it with the help of a figure. Let's say this is, I would use the word hot razor wire. Why I would use the word razor wire? I would explain it in a minute. But this is something which is hot razor wire. You have some system with you. This is your system, and I would just mark it with this dashed line. And then you have a cold razor wire. Now this is your hot body, this is the cold body. You cannot have this flow of heat from this cooler body to the hotter body. You can't have it till the time you do some kind of work on the system. Do you understand what is this graphical representation of that Clausius statement? So this is kind of impossible till the time you do what? Work on the system. And what is the best example for that? Refrigerator. And if you look at pump, what does it do? It basically makes the fluid moving from what? Low pressure to higher pressure, isn't it? So it means it is equivalent to that situation. So it means pump is something which also follows this statement. Understood? Any question? So you can say that Clausius statement is valid for what kind of systems, or it is more apparently valid for refrigerators and heat pumps, right? Although all the other statements are equivalent to it, but for the time being we can use that statement for these two systems. Now let's talk about the next one. Kelvin-Planck statement, right? So this Kelvin, he is the same Lord Kelvin who devised this Kelvin scale, right? That Kelvin scale is named after this scientist, and I hope you have heard about quantum theory, Max Planck, right? So he is the same one, same person. So due to their work, this statement is named as Kelvin-Planck statement. And generally this statement, just like Clausius statement, was apparently more valid for what? Refrigeration systems and pumps. This is more valid for heat engines. By the way, they are valid for all the systems, but more valid which seems apparent. So heat engines. So how do you describe it? It says it is impossible for any system to operate in a thermodynamic cycle. Remember that. You talk about this thermodynamic cycle, okay? And deliver a net amount of work net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. Okay. Now let me again graphically represent it. Now what do you mean by reservoir? Remember that reservoir is kind of an abstract concept. It's an idealization. This reservoir, thermal reservoir, it is an idealization. Now what kind of idealization? You say that it does not matter how much amount of energy is transferred to that thermal reservoir, or let's say how much of energy is extracted from that thermal reservoir, its temperature does not change, just like the atmosphere. Now you can see, for example, if you talk about the whole atmosphere of the earth, or let's say a big sea or lake, you can talk about the energy levels which have, or you can say the amount of energy which has been transferred to those systems, or let's say extracted from those systems. But generally on average their temperature remains the same, right? We don't talk about that uniformly distributed, but yes, on average it would remain the same. It does not matter how much amount of energy you are putting in or you are taking out, but its temperature remains the same. This is an idealization. In practice that does not happen. A small amount of change is there, but not a big amount of change, so we can neglect that. So you talk about that thermal reservoir. So right, so we talk about that kind of idealization for its definition. Okay, so you talk about this, let's say hot reservoir, we have this, and then we have a system. Why I'm putting it like a circle, because I'm talking about thermodynamic cycles. Okay, and then I have this cold reservoir. Now this statement says that it is impossible to define a impossible to define a system following a thermodynamic cycle. It is impossible to design a system which follow a thermodynamic cycles, which can take heat from the hot reservoir and solely convert it into, let me put it this way, QH, heat coming from the hot reservoir to this system. So which can take the heat from the hot thermal reservoir and convert it completely into work. Just look at the statement. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings, while receiving energy by heat transfer from a single thermal reservoir. Now what does that mean? If you do not consider this cold reservoir, is it possible to have this kind of arrangement? Not at all. You can't have that. So a single thermal reservoir, which is the hot one in that case, that doesn't work. To make that system work, you need to do what? You need to have a cold reservoir where this system would extract some kind of energy. It would dissipate some kind of energy to that cold reservoir. Right? So now can you see why you can't convert the whole amount of energy coming to the system into work? You can't have that. You have to dissipate some amount of energy to the cold reservoir, and that is due to what? Irreversibility. That is due to what? Irreversibility effects. Now it doesn't matter how much amount of lubrication you add to some system, still friction would be there, isn't it? You can't make that friction, you can't bring it to a zero level, right? So I hope the point is quite clear.
So not even in the ideal case we can all convert all the heat that our body is receiving from a hot reservoir into the work.
So I hope you are quite clear about those two statements. I told you that those two statements are equivalent. Clausius statement and Kelvin-Planck statement, which are generally used, they are equivalent. It means if you violate one, you would be violating the other. So in your book there is a paragraph which demonstrates how those two systems are equivalent. So that is your reading assignment. You need to understand it yourself, how those two systems are equivalent. I have tried to explain those two statements in detail. Now you need to read that paragraph and understand how it is possible to violate one statement and at the same time you would be violating the other one. Okay, so but if you have any question you can ask me in my office. Now there is something which is the quantitative side of that law, of that statement. Just see, deliver a net amount of energy by work to its surroundings. Deliver a net amount of work to its surroundings. It means that work of a cycle cannot be positive. If you deliver some kind of, if the system does some kind of work on the surrounding, it would be taken as positive. Now it says that in this scenario, if you have a single thermal reservoir, you can't have positive work. Do you understand that? Right? So you can't have positive work according to this Kelvin-Planck statement. Okay, so this is kind of a mathematical representation of it. And obviously we are talking about single thermal reservoir in that case. If you have a single thermal reservoir, this system would have negative, you need to do something on the system. Okay. So that was a reading assignment I have already given you. Okay. So let's talk about the third statement, which is entropy based statement. By the way, this is the most important one. Why? Because that has been used for devising complex engineering systems. You can say more advanced in recent times. That statement has been of great help. Do you know the word entropy? What is that? How do you describe it? Sorry? Amount of what? Something else. It's kind of a measure of disorder, but yeah, I mean, for the time being, I would define it like this: a measure of disorder, right? But at the later stage, we would see more explanation of it, both in the qualitative sense and in the quantitative sense, right? But for the time being, I would just say that it is kind of a measure for disorder. Or you can say this term describes the lack of order or predictability. If I just draw a system, just look at it very carefully. This is the system at state 1, at time 1, let's say, at time equals 1 second. And then after some time, I have this system. Do you think its entropy increases? Do you think its entropy? Its entropy would always increase. And for example, if those time instants are not described, can you say which is occurring at the later stage and which is the initial state? The ordered one would be the initial state and the disordered one would be the next stage, right? So what does that mean? It means entropy always increases with time. Entropy always increases with time. So this is something which is entropy based statement for second law of thermodynamics. Entropy always increases with time. Okay, so that is something which is entropy based statement. Or let me put it this way as well. It is impossible for any system to operate in a way that entropy is destroyed or minimized. It is impossible for any system, right? So those three statements are there. We would talk about in more detail for reversible, irreversible processes and cycles, engines in the next lecture, inshallah. So it is very important to go back and read that theory carefully.